Hello sir, I will cover the topic minimization of DFA. So if we have any DFA and we want to get the minimal DFA, then we have to find the equivalent states. So the states P and Q will be equivalent if there is a transition from state P over string W reaches to the final state, then transition from Q over string W should also reach to any of the final state. Otherwise, if the transition is not reaching to the final state, then Q also should not reach to the final state. If this property holds in P and Q, then we will say that P and Q are equivalent states. So if the length of the string is 0, then P and Q are 0 equivalent. If length of the string is 1, then P and Q are 1 equivalent. So on. If length of the string is n, then P and Q are n equivalent. Now we will take an example and we will solve this. Suppose this is the automata given and we want to convert this DFA into minimal DFA. This is the state transition diagram and this is the state transition table. This is the first state and Q4 is the final state. So the first step of the procedure is we will delete the unreachable state. If it contains any unreachable state, then we will delete that state. Here is no state is unreachable from the start state. Suppose if there will be a state say Q5 from here, so this cannot be reached from the Q0. So if this will be present in the DFA, then we will delete this state initially. Since this is not present in the DFA, I am not taking this. Okay. So the first step is we will delete the unreachable state. Now we will find the equivalency. First we will find 0 equivalent states. So zero equivalent sets can be written into two sets of non-final and final states. Now we will find the first equivalent states. First equivalent. These 4 states are 0 equivalent states. I will check whether these 4 are 1 equivalent or not. Okay. So let's check Q0 and Q1. Q0 on 0, Q0 and Q1. Q0 on 0 is going to Q1. Q1 on 0 also going to Q1. Q1 is in the same set. Q0 on 1 going to Q2, this set. Q1 on 1 is going to Q3, this set. So Q0 and Q1 will be in same set. Both are 1's equivalent also. We will check Q3. We will check Q2. We can check Q2 with any one of them, Q0 or Q1. But let's check Q2 with Q0. Q0 on 0 going to Q1. Q2 also on 0 going to Q1. No problem. Q0 on 1 going to Q2. Q2 on 1 going to Q2, this set, no problem. So Q2 is also 1 equivalent. Now check Q3. Let's check Q0 and Q3. Q0 on 0 going to Q1. Q3 on 0 is also going to Q1, this set, no problem. Q0 on 1 going to Q2, this set. Q3 on 1 is going to Q4, another set. So since Q3 is not going to the same set, so we will separate Q3. Q3 is no more 1 equivalent to these many states. Now we will find 2 equivalent states. We will check Q0 and Q1. Q0 and Q1. Q0 and Q1 both are going to Q1 on 0, no problem. Q0 on 1 is going to Q2, this set. Q1 on 1 going to Q3, another set. Again Q0 and Q1 going to different sets on the input symbol 1. So we will separate these two states as well, Q0 and Q1. These states will be in different sets. Now check Q0 and Q2. Q0 and Q2 both on input symbol 0 going to Q1 and on input symbol 1 both are going to Q2. Since both are going to the same set, there will not be any problem. So Q0 and Q2 will be in same set. Q1 will be in another set. Q3 and Q4. Now we will find 3 equivalent. Okay, if we find 3 equivalent, these are the single elements, so we will not check in these sets. We will check in this set, Q0 and Q2. Q0 and Q2 on input symbol 0 is going to Q1 and on input symbol 1 is going to Q2. No change. So here we get no change in these states. So if we get no change in the equivalent states, then we can say these are the minimal states of the automata. Since these are single and there are two states in the set, so we can use any of the state that will represent this entire set. We can choose Q0 as the representative of this set. So we will replace Q2 by Q0, 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 Q0 and Q0. Since these two rows become equal, Q0 on 0 going to Q1 and on 1 going to Q0, and this is same. So we can erase this entire row. This is Q4. Okay. Now this is the minimal state transition table for this automata. Now we can draw the state transition diagram as well with the help of this table. But now check one thing, how we are getting these 0 equivalent, 1 equivalent. I have said this in the definition earlier. Same. All these four states are not going to the final state together. So these are 0 equivalent, because let the string of length 0 will be epsilon. So these four are not going to these four are not going to final state on symbol epsilon. You can check. But Q4 is going to final state on input symbol epsilon. So these are separate. Let's check one equivalent. One equivalent means the length of a string is 1. That is, by seeing one input symbol, if any state can reach to the final state, then all those states will be grouping. Let's say, see here, why Q3 is separated from this set. See, Q0, Q1, Q2, Q0, Q1, Q2, all three states cannot reach to the final state with input symbol, only input symbol of length 1. But Q3 can reach to the final state by just applying one input symbol, that is 1. So these are one equivalent. Similarly, we can find 2 equivalent, 3 equivalent and equivalent, but there will be no change after the 2 equivalent. So we can say that these are the minimal states. We can draw the automata for this minimal state transition table as well. So if we draw the DFA, we will get Q0. It is going to Q1 on input symbol 0, and it is loop itself on input symbol 1. Q1 on 0 is going to loop itself, and on 1 it is going to Q3. Q3 on 0 is going to Q1, and Q3 on 1 is going to Q4. This will be the final state as well. Q4 on 0 is going to Q1. Q4 on 1 is going to Q0. Okay, so we can see that our initial automata was containing 4 states. Our initial DFA is having 5 states, but our minimal DFA is having only 4 states. So if we follow this procedure, we can get the minimal DFA. Thank you, sir.